algorithm and the proof is even more interesting. So actually, last year, one student asked me about this proof, and then actually I go through it in detail, and there is a benefit of doing that also. Okay, so we will go into this. So basically, the history of this algorithm is as follows. So this algorithm was actually developed by Kuhn, 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 and he named this algorithm as Hungarian algorithm. Now, it apparently feels that the person Kuhn is from Hungary, but the actual story is a bit different. So, what happened that when Kuhn solved this problem, he finds that, hello, yeah. So, am I audible? Am I audible? Internet क्या है? Am I audible?
Yes, sir. Yes.
And this as the slide is visible also?
Yes, sir.
Okay, okay, okay. What happened that Kuhn has developed this algorithm, but Kuhn is not a person from Hungary. So the algorithm he has developed, that is the algorithm that we will discuss today, is developed by Kuhn, but he actually applies the idea of Koenig and Egerferry. So in 1931, maybe the year is a bit wrong. It may be 19. I think it's 1931, but it may be 1935 also. So in that range, in 1930s, okay, 1930s, Koenig and Egerferry has proven that in a bipartite graph, the size of the maximum matching is equal to the uh, size of the minimum vertex cover. Okay, and this proof is basically for unweighted graph. But what Kuhn has actually uh, done a reduction from this weighted bipartite matching problem to an unweighted bipartite matching problem, and he solved that. And according to Kuhn, that this reduction is not that difficult to do. According to him, it's not trivial, definitely. But the tough part was done already by Koenig and Egerferry, who are eventually the scientists from Hungary. So that's why he has given this name is Hungarian algorithm. Okay, so that's just a story or history. It's not important. So basically, today we discuss few more things which I haven't discussed in my. So basically, हम लोग दो प्रॉब्लम यहाँ पे सॉल्व करते हैं. जैसे हम लोग जब when we have solved maximum flow, we also have solved minimum cut problem also. So both problems are dual to each other. सिमिलरली वेटेड बाइपार्टाइट मैचिंग का भी एक डुएल है, दैट इज कॉल्ड, जैसे मैचिंग का डुएल था कवर, कोनिक एगरफेरी प्रूफ दैट मैक्सिमम मैचिंग इक्वल टू मिनिमम वर्टेक्स कवर. और वेटेड मैचिंग के लिए उन लोगों ने जो प्रपोज किया, दैट इज साइज ऑफ द, आई शुड से द वेट ऑफ द maximum bipartite matching in a weighted graph is equal to weight of the minimum vertex cover in a bipartite graph in the same graph. So यहाँ पे एक वेटेड कवर का भी कॉन्सेप्ट आ रहा है, और वो एल्गोरिथम भी हम डिस्कस करेंगे यहाँ पे. तो वेटेड बाइपार्टाइट मैचिंग एंड वेटेड, आई शुड से वेटेड वर्टेक्स कवर, दोनों ही यहाँ पे कवर होगा, एंड वी विल सी हाउ. ओके, नाउ इफ यू रिकॉल द कोनिग-एगरफेरी थ्योरम, उसमें क्या हुआ था? कोनिग-एगरफेरी का थ्योरम का ये था कि he starts with a larger cover, larger vertex cover, and from there he actually reduce that size of the cover, and when it is optimal, we say that the matching is equal to the cover. That is the philosophy of that Koenig-Egerferry theorem. So here we will do this following thing. So first we'll try to understand what is the problem. The problem was as follows. A farming company has 3 farms. यहाँ पे n farms हैं, n यहाँ 3 है in this picture. 3 farms and 3 processing plants. Okay. Now each farm can produce corn to its capacity to the plant. So every farm can use the plant fully, and the profit of farm I, while using plant J is Wij. Now the maximum matching says that the maximum weighted matching problem says that form a matching to maximize this total profit. That means which farm to use which processing plant such that the summation of Wij will be maximum. Okay, and we know this problem, that is called maximum weighted matching problem. Now the interesting part comes, which I haven't covered so far. Suppose the dual problem of this. Okay, now ये farm जब ये corn produce कर रहा था, then government feels that too much corn has been produced, so he has to stop the production. So what he will do, the government claims that too much corn has been produced, so it will pay the company not to process the corn. Okay, so government will pay EY if the company agrees not to use farm oil, and the government also pay VJ to the company if the company agrees not to use plant J. Okay, so what happens here, तो ये सब X जो है ये सब है मेरा farms. So X1, X2, X3, there are 3 farms and Y1, Y2, X are the processing plants. So government क्या कर रहा है, बोल रहा है कि say for example X1, तुम X1 को मत यूज करो, इसके लिए गवर्नमेंट आपको कुछ पैसा दे रहा है. It's same for X2, same for X3. Similarly for Y1, Y2, Y3, government want to give some funds and ask them you don't produce any corn. But कब company राजी होगा? When the company will agree to the government offer. When this maximum profit that is gaining out of the, so maximum profit जो company earn कर रहा है, इतना amount of money अगर government उसको pay कर दे, तो the company कभी भी ये use नहीं करेगा. Are you getting my points? The thing is, company suppose X1, Y2, X2, Y1 and X3, Y3 is the best possible combination to get the highest profit. Now गवर्नमेंट बोल रहा है कि कॉर्न बहुत ज्यादा प्रोड्यूस हो रहा है, तुम लोग प्रोड्यूस मत करो. अगर कंपनी को गवर्नमेंट कोई कॉम्पेंसेशन नहीं देगा, इन दैट केस द कंपनी विल बियर द लॉस. सो गवर्नमेंट हैज टू गिव सम कॉम्पेंसेशन टू द कंपनी, एंड व्हाट शुड बी दैट कॉम्पेंसेशन? That should be greater than equal to the profit that is made by the company itself while using the plants, right, by different farms. Now what government is, government kuch value, so government, what government does, government will pay UI if the company agrees not to use farm oil. Also the company will pay VJ if the company agrees not to use plant J. Now if UI plus VJ, ये जो company दे रहा है, if that is less than equal to Wij, then the company makes more by using the XIYJ than by taking the government offer. So in order to stop all the production, what the government should do? Government must offer some amount such that this UI plus Vj must be greater than equal to Wij for all Ij. For all Ij, UI plus Vj is greater than equal to Wij. In that case, the company won't use their farm or their processing plants because usko government से compensation मिल ही रहा है. So there is no point in producing the corns. So the minimum weighted cover problem is what the government wants to pay. So what is the values of UIs and VJs that should be given by the government to the company such that the total UI plus VJ would be minimum. So जैसे स्मॉलर एग्जांपल मैं यहाँ पे दे रहा हूँ, ये सपोज मैं 2 प्लांट ले रहा हूँ एंड 2 फार्म ले रहा हूँ एंड 2 प्रोसेसिंग प्लांट ले रहा हूँ and I put some arbitrary values to them. And suppose this is the cost. Suppose this cost है 1, maybe it is 2. This is 7. This is 5. This is 6. So the maximum matching will be this. Okay. So it will be 7 plus 5, 12. Now what government should pay? अगर गवर्नमेंट सपोज कंपनी को दे रहा है 8 रुपीज, सपोज 2 plus 6 is 8, then company will say that I will, this is my farm 1, suppose it is F1, this is my farm 2, this is my processing plant 1. So then government, then company says that if you give me the compensation 8, then what I will do, I will get a better profit by if the farm 1 use P2 and the farm 2 use P1. So government has to place 12 amount of money. It may give more. Say for example, to stop farm 1, it has given say it is 5. So this is also 5. This is 5. तो गवर्नमेंट उसको बोल रहा है कि तुम अगर फार्म 1 यूज नहीं करोगे, आई विल गिव यू ₹5. If you don't use F2, I give you ₹5. Say for P1 and P2 also. So he pays 20. So what the company says that I get maximum profit 12, but company gives me 20. So it is a better option that not to produce the corn. But it is the loss for the government, because government can give them to 12. So basically, if you look from the perspective of so what is the company's perspective? Company's perspective to increase this profit through this matching, and the objective of the government is to reduce this cover. So F1, F2, P1, P2, this is basically the vertex cover. You want to reduce this cover, weighted cover, such that company won't produce any more corn. Okay, and when the optimality reaches, when maximum weighted matching equal to minimum weighted cover. Okay, so what will be the ultimate cost? ये यहाँ से फिगर आउट करना थोड़ा सा मुश्किल है, बट से इसको मैं अगर 7 कर देता हूँ, 7 0. ये नहीं हो सकता because it is 1. This is 6. And then 0. 5. And this might be 1. So this may be the offer. So farm 1 को गवर्नमेंट 1 रुपया दे रहा है, प्रोसेसिंग प्लांट को 5, प्रोसेसिंग प्लांट 2 को 6. So अभी if you look into this, आप देखोगे कि say 5 plus 1 6 that is produced by it. So farm 1 won't use P1 क्योंकि इसको यहाँ पे प्रॉफिट मिल रहा है 2 और यहाँ पे अगर ये यूज नहीं करेगा तो 5 plus 1 6 मिल रहा है. So 6 greater than 2. Similarly, farm 2 won't use P1. अगर वो यूज करेगा तो उसका प्रॉफिट होगा 5 और गवर्नमेंट ऑलरेडी P1 के लिए 5 दे रहा है तो 5 plus 0 is 5. Similarly, 6 plus 0 is 6. Similarly, 1 plus 6, 7 equal to 7. So in each case, for each age, I see that, so these are my UIs. Okay. So this is U1, U2, this is V1, V2. So I see that for all ij, what I'm seeing here, for all I and j, Ui plus Vj is greater than equal to Wij. And since this is given by the government, so the company won't use it farm or any processing plant to produce the corn. Okay. Now the best offer is, this is the optimal assignment. If you see here, this is the optimal assignment. यहाँ पे minimum cover है this 5 plus 6 plus 1. So that is the offer given by the government, that is equal to 12. Also the maximum weighted matching is 7 plus 5, 12. So this is the best combination. Okay, and this is optimal solution. So that is what we are trying to say. So basically what I am trying to say is government wants to minimize its contribution to the company and company wants to increase its profit. So increase its profit means basically maximum weighted matching. So weighted matching जो है इसको it tries to maximize it. Similarly यहाँ पे minimum cover जो है इसको ये minimum करना चाह रहा है. So government want to pay less. So the government wants to find such value of Ui and Vj such that so as to minimize summation of Ui and summation of Vj. And optimal happens here. For a perfect matching M and cover UV in a weighted bipartite graph, CUV means cost of the cover. That is 12 in this case, in this example. Cost of the cover is always greater than equal to weight of the matching. Okay. And it will be equal if and only if the matching consists of the edges xi, yj such that ui plus vj equal to wij. Okay. And so it is only true for matching edges. ये जो matching edges है देखिए 5 plus 0 equal to 5, 6 plus 1 equal to 7 equal to 7. Okay, so that is being written here. Okay, at optimal it is CUV equal to WM and if and only the edges in the matching consist Ages in the matching is such that ui plus vj must be equal to wi, and in such case the perfect matching m and the weighted cover uv are optimal. Okay. इसका प्रूफ है, बहुत छोटा प्रूफ है, मैं वो प्रूफ यहाँ पे डाला नहीं हूँ. Maybe I will put it later and I will send you the slide. But ये प्रूफ बहुत छोटा है and it's very obvious. And the proof is the same line कि initially government ज़्यादा पे कर रहा है and it can so suppose it has a maximum matching. When it has a maximum matching, all the vertex are being so at this stage it is the maximum matching. So all, and it is a perfect matching also. So, and in this case all the vertex got, so all vertices got saturated. Okay. And the perfect matching is maximum. So what happens? So what the government will do? Government will assign such values of UN and VJ such that it should be equal to this value. Because इससे कम value offer करेगा तो it will always get a better matching. So it will produce corns. Okay. So it actually says that the government, what should say, the UI and VJ values should be such that their summation is equal to the maximum match, weight of the maximum match. Now we'll actually go to an example and we'll try to illustrate how this cover and matching can be found out. So this algorithm is actually finding out. So in a weighted complete bipartite graph, the minimum weight cover UV, why it is called UV? U means, so basically when I'm saying U means basically U is a vector. U is a vector which consists of here 1 and 0, and V is a vector that consists of 5 and 6. Okay, it is not a single variable. Basically, they are the vectors. Okay, so in a weighted complete bipartite graph, the minimum weight cover UV is equal to the maximum weighted perfect matching M. So initially, ये जो matrix दिया गया है मुझे, suppose this matrix is given to me, and somebody asked me to find the maximum weighted matching, or in other words, the minimum weighted cover. दोनों ही निकालने के लिए बोला है. So what we will do in this algorithm? For each row, we find the maximum and we assign it is U1. So U1 is basically 6 because it is maximum. Here it is 7. Here it is 8 because it is maximum in this third row. In fourth row 6 is maximum, fifth row 8 is maximum. Now if we put this value, you have to note that okay, this is a cover. This is not a minimum weighted cover. This is a cover. Why? Because so what is this value? This is x1 y1, that is 4. Okay, so u1 plus v1, that is 6. 6 is greater than 4. Since I take it as the maximum value, so always ui plus vj must be greater than or equal to this value. It is 6 plus 0 equal to 6. Okay, यहाँ पे 6 plus 0 greater than 2, 6 plus 0 greater than 10. It will always happen. So this is a cover. So this is the way we create a cover, and it will be always true. If we find the maximum value of each row and we assign them as ui's. So ith row का maximum अगर मैं ui में assign कर देता हूँ, and all vj's will be 0, then definitely it is a cover. But here what is the amount government has to pay? 6 plus 7 13 plus 8 21 plus 27 plus 8 35. So 35 is the cost that it has to pay. Okay, but the question is, can government pay less than this? The answer is yes, and that will be found through this maximum matching business. Okay, then how do we do this? So now to solve this problem, to what is the algorithm? So there is a concept of a equality subgraph. What is the equality subgraph? The equality subgraph of for a cover UV is a spanning subgraph of KNN such that having the edges xy, yj such that uy plus vj equal to wij. The edges of that equality subgraph corresponding to zeros in the excess matrix and all this stuff. Okay, so what they actually say is, so this is my matrix. Okay, now from here I will create an excess matrix. What is that excess matrix? So this is our original matrix that is given as input. Okay, so this matrix is given as input, then we run an algorithm to populate ui values, and vj's are initialized to 0. Then what we do, for each cell of the matrix, we create excess. What is excess? ui plus vj minus wij. So 6 plus 0 minus 4, that is 2. 6 plus 0 minus 1, that is 5. 6 plus 0 minus 6, that is 0. So that we have done here. 6 plus 0 minus 4, 6 plus 0 minus 1, 6 plus 0 minus 6. So here 4, 1, 6, 2, 3, these are the original matrix. 4, 1, 6, 2, 3. If you look here, 4, 1, 6, 2, 3. यहाँ पे 4, 6, 5, 8, 6. 4, 6, 5, 8, 6. तो यहाँ पे हम क्या करें? 8 plus 0 minus 4. 8 plus 0 minus 6. 8 plus 0 minus 5. If we do this, then we get an excess matrix, and this is this excess matrix. So I won't mention UI. So basically 6, 7, 8, 6, 8, this is there, and this is zeros, and this is the excess matrix. We called it an excess matrix. Abhi excess matrix mein, so this is the reduction that is done by Kuhn. Okay. Now what this actually gives? It gives some values as 0. Now what you do, so this matrix is copied here, this matrix is copied here, and these are the zero. So and the rows are xi, so x1, x2, x3, x4, x5. So these are the rows, and these are the zeros are the columns, y1, y2, y3, y5. So 0 के corresponding मैं एज को प्लॉट करूं, तो व्हाट इज दिस? दिस इज फ्रॉम x1 टू y3. सो x1 टू y3. सो ये एजेस जो है दैट कोरेस्पॉन्डिंग टू 0 इन द एक्सेस मैट्रिक्स. देन यू लुक इनटू हियर दैट x2 to y4, x2 to y4, then x3 to y5, then this one is x4 to y3, x4 to y3, and this is x5 to y4, x5 to y4. These are the zeros. Now what we do here, now this graph is an unweighted bipartite graph, right? And we know the algorithm how to find maximum matching in unweighted bipartite graph. I am not going to discuss how we do this. We have already know this. It is known to us during our algorithm course. Okay, so we know that. So this is the maximum matching. Okay. Now, from Koenig-Iger-Vary theorem, I know that in a bipartite graph, maximum matching equal to minimum cover. So यहाँ पे क्या है कि from this we can find the minimum cover also. How? You can use the Koenig-Iger-Vary theorem. So अगर आप Koenig-Iger-Vary theorem का प्रूफ करोगे, आपको पता चल जाएगा कि कैसे हम लोग ये मिनिमम कवर इससे निकाल सकते हैं. ओके, तो यहाँ पे मिनिमम कवर होगा y3, y4 and x3. So that will cover all the edges of this graph. Now what this means, हम लोग जो असाइनमेंट प्रॉब्लम पढ़े थे वहां पे हम लोग हर एक लाइन को काट कर रहे थे. If there is a single zero, I cut the corresponding column. So basically what we are doing there, actually we are finding this matching, that cutting the rows or cutting the columns that we are doing in that assignment problem, that is nothing but finding this matching. Okay, so यहाँ पे हम लोगों ने जो कवर मिल गया है कि y3 y4 and x3 अगर मैं सिलेक्ट करता हूँ, I see that all the edges will be covered. So that is this row. You see that इस रो में एक जीरो है, तो हम लोग कोरेस्पॉन्डिंग कॉलम को काट देंगे. So that is why this is my y3. So that is why y3 is. Then there is a single zero in this row. I cut this corresponding column, so this is a single t. So that is why y4 is selected. Then यहाँ पे सिंगल जीरो हम इसको भी काट सकते थे, बट हम लोगों ने ये नहीं काटा है. दैट इज ओके. हम लोगों ने ये देखा कि इस कॉलम में एक जीरो है, तो हम इस रो को काट देना है, तो इस इज आर. So there are multiple ways. Basically our objective is with minimum number of lines I can cover all the zeros in this matrix. Basically it actually says finding the matching, finding the maximum matching in the unweighted bipartite graph. Now the thing is, हम लोग इसके बाद चेक कर रहे थे कि whether the size of the matching is equal to the order of the matrix. The answer is no. That means few things can be done. Okay, so that is something. So इसके बाद हम लोग क्या किए थे कि the uncovered जो part था उसमें minimum लिए थे. So when we use this row, so we cut this two rows and I cut this, we cut this columns, third column and fourth column, and third row we have been cut. तो बाकी uncut जो elements है उसमें मैं minimum लिया था 1, and that 1 is being subtracted from this uncovered element and 1 is being added to these junctions. Okay, that is something we have done, but the question is what it actually means. अगर आपको याद है what we have done कि जैसे ये 2 5 2 7 they are not covered by any line, so and 2 5 2 7 3 1 यहाँ पे 2 2 यहाँ पे 3 2 2 4, basically which elements which are uncovered by the line उसका मैं minimum लेता, and that turns out to be 1, and I subtract 1 from each of them. And ये 4 and 3 जहाँ पे ये overcross कर रहा है, t t यहाँ पे जा रहा है, r यहाँ पे जा रहा है, so these are the junction points where two lines crosses. So 4 becomes 5, 3 becomes 4, and this 3 became 2, this 1 became 0. That is something we have done. Now what does that mean? ये क्यों हम लोगों ने ये चीज किया था? That was the question at that time, and we haven't answered that question. So we try to answer this question here. So GUV is an unweighted bipartite graph. If GUV has a perfect matching, then its weight will be summation of ui and summation of vj, and by the equality lemma, जो lemma हम लोगों ने mention किया था without proof, we have the optimal solution. But in this case we don't have a perfect matching, but we have a matching, and we have a vertex cover, and they must be of the same size, and that is known from the Koenig-Iger-Valley theorem. Now R is the set of vertices from the, so ये जो cover है Q, इसमें कुछ vertex, some vertex are being taken from x partite, some vertices are taken from y partite. So R is that set of vertices which are taken from x partite, and T is the set of vertices that are taken from y partite. So यहाँ पे x3 is taken from x partite, and y3 y4 they belong to T, they are taken from y partite. So our matching consists of mod q, our matching of size mod q consists of r edges from r to y minus t and t edges from t to x minus r. Okay, so matching is r edges, r मतलब x3 एक ही एज है यहाँ से x3 to x5 y5, or t edges, that means there are two edges, mod t edges, y3 to x1 and y4 to x2. mod t edges from t to x minus r. ओके, सो ये चीज देखो, ये r है, r से this y1 y2 and y5, this is basically capital Y minus t, इसमें एक ही एज सिलेक्ट हुआ है. सिमिलरली mod r edges from r to y minus t, and mod t edges, mod t in this figure, that is two edges from t, that is y3 y4 से to x minus r, two edges from t to x minus r. Okay, so our matching size is mod q. Now our objective is, हम लोगों को परफेक्ट मैचिंग नहीं मिला, we haven't got perfect matching. So our objective is to increase, to seek a larger matching in the equality subgraph. We change the cover UV, to introduce an edge from x minus 1 to y minus t while maintaining the equality on all the edges of M. So what is the thing that we have to do? At this stage we get a maximum matching, but it is not a perfect matching. तो हम लोगों को करना क्या पड़ेगा? We have to introduce few edges. Now we need to introduce edges from x minus r to y minus t. x minus r कौन सा vertex है? x1 x2 x4 and x5, and y minus t कौन है? y1 y2 and y5. इनके बीच में एज मुझे इंट्रोड्यूस करना पड़ेगा. Why? Because in that case only you can increase the size of the matching. Otherwise what happened? Suppose अगर आप x and y minus t में x3 is already selected, so if you introduce any edge here, it doesn't increase the size of the matching, because already it is being covered by this vertex. Suppose x3 से मैं y2 y1 y5 सबको खींच दिया, but already it is a minimum cover. Similarly y3 से अगर मैं x3 या y4 से मैं x3 को खींच दिया, या y4 से x4 खींच दिया, this edge won't help to increase my cover, won't help to increase my matching. So मुझे ऐसे edges introduce करना है, जैसे y2 to x5, y2 to x4, this kind of edges. That means from y minus, to seek a larger matching in the equality subgraph, we change the cover to introduce an edge from x minus what to y minus t while maintaining the equality on all the edges of M. So without changing the existing matching M, so why say while maintaining equality on all edges of M means excess matrix में जो so why these edges are coming here? Because they corresponds to 0 weight. So our objective is to introduce more edges from y minus t to x minus r such that they are of 0 weights. Along with that, these 5 edges also should be 0. And how we can do that? We can do that by manipulating these values 6, 7, 8 and 0, 0, 0. Okay. So try to understand. Now our objective is to introduce more edges from x minus t to y minus r. And these edges can be introduced means they must be of 0 weight. Because हम लोग ये unweighted bipartite matching यहाँ पे use करेंगे. We are going to use unweighted bipartite matching out here. So we have to introduce such an edges without compromising the earlier graph. तो ये 5 edges तो रहेगा, उसके साथ भी मुझे edge introduce करना पड़ेगा. The question is how do we introduce that? To introduce that, हम लोगों ने ये लिया था कि जो लाइन कवर नहीं कर रहा है, जो एलिमेंट्स आर नॉट कवर्ड बाय दिस कटिंग लाइंस, उसका मैं मिनिमम ले रहा हूं, एंड दैट विल बी सबट्रैक्टेड फ्रॉम देयर एंड दैट विल बी एडेड टू दिस जंक्शंस. And you see, and we have proved today, then why that will help us. That is the motto of this discussion today. So a cover requires अगर जब हम कवर बोल रहे हैं, we know that ui plus vj must be greater than equal to wij for all ij. That we know. And M consists of edges xi yj such that xs ij equal to 0. ui plus vj equal to wij in all these cases. Last matrix में अनवेटेड ग्राफ में ui plus vj equal to wij था, इसीलिए वो सब edges will be introduced. The difference ui plus vj minus wij is the xs. Okay. Edges joining x minus r and y minus t are not in GUV. And why that is so? Because they have positive x's. That is why they are not there in the earlier graph. Now epsilon is the minimum x's among all those edges from x minus r to y minus t. Okay. Then what we do, we know that we reduce ui by epsilon and we increase vj by epsilon. So we reduce ui by epsilon for all xi that belongs to x minus r. And what we do, we increase vj by epsilon for all yj belongs to t. So what it says, okay, so these are the lines, these two lines and this line. So uncovered जो element है उसमें 1 is minimum, so 1 will be added to, sorry, 1 will be subtracted from x minus r. So ये 6 became 5, 7 became 6. This is a line, so it is not being done, it remains 8. This became 5, this became 7. And t की जो line है, this will be 1 and this will be 1. So this will be 0 plus 1, this will be 0 plus 1. So what it says, okay, 1 is subtracted, the minimum excess epsilon is 1 here, that is subtracted from all the x minus r values for all ui where I belongs to x minus r, and we add epsilon to all vj's where j belongs to t, where xj belongs, sorry, yj belongs to t. तो ये 0 plus 1 हो जाएगा, यहाँ पे 6 minus 1, 7 minus 1, 6 minus 1, 8 minus 1. So what it turns out to be, मैं आपको फर्स्ट, मैं एक बार जो एल्गोरिथम है ये आपको दिखा देता हूं कैसे ये काम कर रहा है. So u1 becomes 6 minus 1 equal to 5, u2 becomes 7 minus 1 equal to 6, u3 become 8, u3 remains 8. ये v3 and v4 1 बन गया. Now you see that what is the total value, 5 plus 6 11 plus 8 19 plus 5 24 plus 7 31 32 33. So earlier this cover was 35. Earlier this cover was 35, now it became 33. So with this manipulation you see that the cover value got decreased, but we have to ensure that it does not violate the matching condition. Okay, so what we do, ui plus vj minus wij. So 5 plus 0 minus 4. 4 is the original matrix that is given to us, that is our input matrix 4 1 6 2 3. अगर मैं पहले चला जाऊं 4 1 6 2 3, so ये जो माइनस के बाद है ये ओरिजिनल मैट्रिक्स रिमेन सेम 4 1 6. So ui plus vj minus wij I calculate and I get this value. So 5 minus 4 that is 1. यहाँ पे कोई random ले लो, 8 plus 1 9 minus 4 that is 5. So this became 5. So यहाँ पे 5 6 8 5 7 हो गया, यहाँ पे 0 0 1 1 0 हो गया. अभी ये ट्रांसफॉर्मेशन के बाद यू लुक व्हाट हैपेंस. ये जंक्शन कौन कौन सा था, ये तो t वैल्यू था और ये मेरा r था. These are the junction points. So यहाँ पे 1 and 1 will be added. So it will be 5, it became 4. You look here. This became 5, this became 4. And all other values got decreased. This earlier was 2, it was 5 earlier. So if you look here, just for your satisfaction, I will show you. It was 2 and 5, it was 2 and 7. So it became 1 and 6 here. It became 1 and 6 here. Okay. Now the question is why we do this. वो मैं लास्ट में आप लोगों को आंसर दूंगा क्यों, मतलब what happens. So इससे क्या होगा, कुछ ज्यादा zeros इंट्रोड्यूस हो गया. Now I copy this matrix in the next slide, and I see that I in the earlier graph, earlier equality subgraph, I have these 5 edges. Okay, so x2 y5 was not there, x2 y5 was not there, but all five edges are there in the last iteration. This x2 y5 is newly introduced, but even if it is introduced, the size of the matching is 3 and it is not yet increased. So in the iteration, हम लोग जब पिछले बार पढ़े थे, when we read the assignment problem last time, we see that even the iteration is progressing, but in some cases in both the iteration the size of the matching remains same, and we see that. So एक क्वेश्चन नेचुरली आ रहा था कि सर ये का फॉरएवर चलता रहेगा, whether this algorithm will run forever. So with this manipulation also it will, no, it won't run forever. The reason is the cover size is decreasing every time, and it cannot decrease infinitely minor time because it is bounded by the size. So the cover is decreasing at every iteration. In the first iteration it was 35, in the iteration it is 33, and when it will be stopped, it will be stopped when it reaches the maximum matching. Okay, so in every iteration, even if the size of the matching remains same, the size of the cover is strictly decreasing. Okay, and we'll see why why this is true. Now once this is done, again since it is an annotated bipattern, we find the vertex cover also. So that is why this is T. So these 3 lines are being drawn. So these elements are uncovered and minimum is 1 among them. So amongst them 1 is the minimum. So what we do actually in our assignment problem, हम लोग ये 1 सबसे delete कर दिए थे, 1 decrease किए थे, so it became 0 3, it became 0 5, it became 5 4, it became 1 0, it became 2 0, and it remains same because there is no crossing of lines. Okay, that is something we have done. Now यहाँ पे हम लोग क्या कर रहे हैं, यहाँ पे हम लोग ये बोल रहे हैं कि if there is something in, so there is no R here. Okay, so here R set is null. So x minus R में जितने भी हैं उसे 1 में घटा दूंगा. तो x minus R में है 5 6 8 5 7. So 5 minus 1 6 minus 1 8 minus 1 5 minus 1 7 minus 1 will be 2. And t के लिए मैं सबको एक एक इंक्रीज कर दूंगा. This will be 2, this will be 2, this will be 1. So t के corresponding जो एंट्रीज है that will be increased. So what I am telling right now, how I update ui and vj in every iteration. For all x minus r, since r is null set here, there is no vertex from x partite is selected as a vertex cover. So r is null. So x minus r is basically the whole x partite. For all of them, I reduced this value by the minimum amount, that is 1. And for t, I will increase them by 1. So this will be 2, this will be 2, this will be 1. Okay, and it will be reduced by 1, and this will be 2 2 1, and I do the same thing, 4 plus 0 minus 4. So this 4 5 2 3, this is the original matrix, and I get this new matrix here. Okay, now you see there what is the total cover cost. 4 plus 5 9. So first it was 35, then it became 33. Now you see that what it is. 4 plus 5 9, plus 7 16, plus 4 20, 26, plus 5. 26 plus 5 is 31. Okay. Now you see that there is a perfect matching. Now you see that there is a perfect matching. So the algorithm stops here. And what is the values? What are the values? The values are this. Okay, so so the matching edges gives you the value. x1 is matched to y3, x1 is matched to y3, तो ये वैल्यू आएगा 6. तो 6 5, so अभी ये देखो इसका ये मेरा ओरिजिनल मैट्रिक्स था. तो 6 plus 5 11 plus 8 19 plus 4 23 plus 8 31 and also this is 31. So ये मेरा what is my minimum weighted cover? This is my minimum weighted cover. That means government will pay 4 units of money to farm 1, 5 units of money to farm 2, and so on. And similarly, it will pay 2 units of money to plant 3, 2 to plant 4, and 1 unit of money to plant 5. Okay. So this is 31 and this is why it is maximum matching equal to minimum cover. So maximum weighted matching equal to the minimum weighted cover. Now we will go to the proof of the algorithm. Okay, why this is correct? So हम लोग क्या कर रहे थे? So the thing that only remains to, there are two things that remains to prove. The first thing is the epsilon adding and subtracting. जो मैं ui से epsilon subtract कर रहा हूँ and x minus r में जो वर्टेक्स हैं उसके कोरिस्पॉन्डिंग ui को मैं डिक्रीज कर रहा हूँ एप्सिलॉन से. सिमिलरली t के कोरिस्पॉन्डिंग जो वर्टेक्स हैं उसके vj को मैं इंक्रीज कर रहा हूँ बाय एप्सिलॉन. नाउ व्हाई दिस इज, मतलब क्यों मैं कर रहा हूँ ये? So basically we read these lines. Okay, so edges joining x minus, so basically when in the earlier slide, so we if it is a perfect matching we will stop. If it is not a perfect matching, we get a matching, we get a maximum matching, and we know that the maximum matching equal to the minimum vertex cover. So R is the set of vertices from x partite, T is the set of vertices from the y partite. Now we have to introduce edges between x minus r and y minus t. To do that, to seek a larger matching, what we do? We do as follows. We reduce ui by epsilon for all the vertices that are in x minus r. Also, we increase vj by epsilon for all yj belongs to t. Now, and we claim that if we do this, so suppose uv is my current cover. What is uv? uv is basically this. This is my u vector, this is a v vector, that is my uv. And वो एप्सिलॉन डिक्रीज करने के बाद ये नए u और नए v बना है. तो पहले uv का समेशन था 35, न्यू uv का समेशन है 33. That is u prime v prime. So suppose uv is the current cover जिसका cost है 35, and that the equality subgraph has no perfect matching. Let u prime v prime denote the new list of numbers assigned to the vertices corresponding to u and v. So u prime is the new vector, v prime is the new vector. And what is u prime? U prime is nothing but ui reducing ui by epsilon for all xi belongs to x minus r. And what is v prime? V prime is basically increasing vj by epsilon for all yj belongs to t. So that is the new u prime v prime. Because अच्छा, तो ये चीज हमको समझ में आया. फर्स्ट आइटरेशन में uv था, एप्सिलॉन डिक्रीज एंड इंक्रीज करने के बाद u प्राइम v प्राइम मुझे मिला है नए वेक्टर्स. Because epsilon is minimum of a non-empty finite set of positive number, epsilon must be greater than 0. That is true, right? Why epsilon is always greater than 0? Because epsilon is taken from the non-covered lines. जो line था व्हाट इज एप्सिलॉन? ये लाइन में कट कर दिया, ये लाइन में कट कर दिया, ये लाइन, so zero is covered by all these lines. How it is covered? Because of this vertex cover. So y3 y4 it will cover all these four lines, 1 2 3 and 4 lines, and x3 cover this line. So all these zero lines are being covered, and epsilon is the minimum of the rest, so epsilon must be strictly greater than 0. Okay, so we have to verify that जो uv को मैं चेंज करके u प्राइम v प्राइम कर दिया बाय मैनिपुलेटिंग दिस एप्सिलॉन, मुझे देखना है कि स्टिल ui prime plus vj prime, initially ui plus vj greater than equal to wij था when we start the algorithm. It was 35 and for all cases it is true. Why it was true? Because ui are taken as the maximum of that corresponding row. So always u and vj stands for 0. So ui plus 0 greater than equal to wij for that row itself. So always it was true when we start the algorithm. Now I change the u and v's in this form to get ui prime and vij prime. We have to prove that ui prime plus vj prime is greater than equal to wij, because it means that ui जो नए u prime v prime मुझे मिला है, that is also a valid cover. But the benefit is it introduce more edges to the equality subgraph. Okay, so मुझे चार चीज देखना है. तो the change of levels on vertices x minus r and t. तो x minus r में जो vertices था उससे मैं एप्सिलॉन घटाया हूं, और t में जो vertices था उसमें एप्सिलॉन ऐड किया हूं. तो उससे क्या हुआ है, ui prime plus vj prime. What is ui prime? ui minus epsilon, and vj prime is vj plus epsilon, where ui belongs to x minus I and vj belongs to t. So ui prime plus vj prime equal to ui plus vj for all the edges xi yj from x minus r to t. So इसका ui vi का जो वैल्यू पहले था, so basically the same summation remains. Okay, so ui prime plus vj prime is equal to ui plus vj. So in the next iteration also x minus r to t में जो edges थे उसमें ये कंडीशन वायोलेटेड नहीं हुआ है. अभी हम देखेंगे r एंड y माइनस t में क्या हुआ है. r में पहले ui प्राइम था, अभी वही ui है. सो एप्सिलॉन में किससे घटाया हूं? एप्सिलॉन इज रिड्यूस्ड फ्रॉम x माइनस r. r से तो मैं एप्सिलॉन नहीं घटाया हूं, सो ui प्राइम रिमेन्स ui. सिमिलरली मैं t को इंक्रीज किया हूं एप्सिलॉन से. सो y माइनस t में जो भी वर्टेक्स है उसमें आगे भी vj था, अभी भी vj है. सो ui प्राइम प्लस vj प्राइम इक्वल टू ui प्लस vj. सो यहाँ पे भी इक्वालिटी सबग्राफ चेंज नहीं हुआ है. आगे ui प्राइम प्लस vj प्राइम, तो ये दोनों केसेस में इट वैलिड्स. थर्ड केस इज द वर्टेक्स व्हिच आर इन r एंड द वर्टेक्स व्हिच आर इन t. यहाँ पे ui प्राइम प्लस vj प्राइम क्या हुआ है, r के जो वर्टेक्स थे उसका एप्सिलॉन में चेंज नहीं किया. सो आई हैवंट ऐड एप्सिलॉन टू द वर्टेक्स व्हिच आर इन r. मैं एप्सिलॉन किसका ऐड किया, x माइनस r में जो वर्टेक्स था उसका मैं एप्सिलॉन ऐड किया, पर r में जो वर्टेक्स था दैट रिमेन्स सेम. सो ui प्राइम रिमेन्स ui, बट yj बिलोंग्स टू t में vj प्लस एप्सिलॉन हो गया है. So earlier it was ui plus vj, abhi it becomes ui plus vj plus epsilon. Now the thing is, since ui plus vj in the earlier iteration is greater than equal to wij, and since epsilon is strictly greater than 0, so ui plus vj plus epsilon, that is also greater than equal to wij, right? So ui plus vj greater than equal to wij. So ui plus vj plus epsilon, that is also greater than equal to wij, because epsilon greater than strictly greater than 0. So ui prime plus vj prime is greater than equal to wij. So that means the weight remains covered. Still the weight remains covered with this transformation. The last is the edges between x minus r and y minus t. So x minus r में जो ui था उसका ui घटा है, so it becomes ui minus epsilon. अभी जो ui प्राइम है दैट इज ui माइनस एप्सिलॉन. yj जो y माइनस टी में था, t का yj मैं इंक्रीज किया, बट y माइनस टी में जो भी वैल्यू था vj का, दैट रिमेन्स सेम. सो vj प्राइम and vj will be same for yj belongs to y minus t. So what is ui prime plus vj prime? This is ui minus epsilon plus vj. So ui plus vj minus epsilon. Now what I do, I add wij and subtract wij to both here, so it remains same. So wij is being added here and wij is subtracted here. So it remains wij plus ui plus vj minus wij minus epsilon. I can write it like this, and I claim that this value ui prime plus vj is still greater than equal to wi. And why that is true? The reason is ui plus vj minus wij minus epsilon, this is strictly greater than equal to 0. Okay, now why this is true? ui plus vj minus ui plus vj, it was the value of ui vj in the earlier iteration, and wij is constant because this is my input. And what is epsilon? Epsilon is नॉन कवर्ड एलिमेंट में जो अनकवर्ड एलिमेंट में जो सबसे मिनिमम वैल्यू था, दैट इज एप्सिलॉन. दैट इज व्हाई ui plus vj minus epsilon ये एक पॉजिटिव एक्सेस है. दिस इज द पॉजिटिव एक्सेस amongst which the minimum value is epsilon. तो इसका ui plus vj minus wij minus epsilon, इसका वैल्यू मिनिमम हो सकता है 0, 0 से ज्यादा भी हो सकता है. So that is why this is greater than equal to 0, because we choose epsilon in such a way. It is the minimum value of the uncovered element. So since it is, this whole thing is greater than equal to 0, so ui prime plus vj prime is basically wij plus this something which is greater than equal to 0. So that is greater than wij. So in all cases we find that we get a reduced cover, but more edges are introduced while the cover condition is not violated. So that is the proof why we do this. Okay, so now so basically in each iteration what we do, in each iteration ये एक अनवेटेड बाइपार्टाइट ग्राफ है जिसमें परफेक्ट मैचिंग नहीं हुआ है. We need to introduce more edges, and which edges? That edges should be correspond to 0. To do that, we manipulate ui and vj in such a way that the cover condition, that is ui plus vj greater than equal to wij, always maintains for all ij. Still it introduce more edges to it. So basically हम लोग कवर की जो वैल्यू है वो एक हायर वैल्यू हम लोगों ने मान लिया है 67868. It is a cover. We can do the other way around also. मैं अगर इसको सब 0 कर देता हूं और सभी कॉलम का मैं एक मैक्सिमम ले लेता हूं, that also will be a cover. We can do that also. We have a cover and our objective is to minimize the cover value, and it will be optimum when the maximum matching equal to minimum cover. Okay, so cover value मैं जब reduce कर रहा हूं, more edges will be introduced here. Okay, so the Kuhn's contribution was how to manipulate this ui and vj such that the cover condition remains valid. उसके बाद उसने ये जो चीज अप्लाई किया, that is actually invented by Koenig and Nigarvari, and Kuhn thinks that this part was much more difficult to prove maximum matching equal to minimum cover. That is why Kuhn says that he gave the name Hungarian algorithm. Okay, and तो 31 वेट आ गया है. अभी इसका प्रूफ है, प्रूफ मैं बता दिया हूं, फिर भी मैं जस्ट द हंगेरियन एल्गोरिथम फाइंड्स मैक्सिमम वेट मैचिंग एट ए मिनिमम कॉस्ट कवर. So the algorithm begins with a cover uv. It can terminate only when the equality subgraph has a perfect matching, which guarantees that equal value of current matching and the cover. So that is this proof is from the lemma 2, that maximum matching equal to minimum cover, maximum weighted matching equal to minimum weighted cover. That is coming from द लेम्मा, जिसका प्रूफ मैंने नहीं दिया, वो 3-4 लाइन का प्रूफ है, वो बड़ी बात नहीं है. नाउ एवरी आइटरेशन में क्या है, सपोज यूवी इज माय करंट कवर एंड द इक्वालिटी सबग्राफ डजंट हैव ए परफेक्ट मैचिंग. तो हम लोगों ने क्या किया, वी लेट u prime v prime be the new vector we get while manipulating. So u is changed by for some u. So basically if the vertex is belongs to x minus r, then u prime is basically u minus epsilon. If v belongs to t, then v prime equal to the vertices in t minus epsilon. Okay, so I get a new cover and we have to prove that this, and we have proven that u prime v prime जो मैंने मिला, that still u and v change to u prime and v prime, which is a yet minimum cover, and we get and that is a valid cover. That is something we have proven here. Valid cover means ui plus vj greater than equal to wij in the earlier iteration. In the new iteration also, ui prime plus vj prime, which is the new values, they are also greater than equal to wij. And last, we have to prove that the algorithm must terminate, and it is terminating when equality subgroup has a perfect match. Okay. Now at each iteration, what happens? We reduce the cost of the cover by an integer amount. Since the cost starts at some value, some higher value, and is bounded below by the weight of a perfect matching. So after finitely many iterations, we have this equality. Okay. So this last slide actually proves that this algorithm will terminate. ये perfect matching वाला business repeatedly चलता नहीं रहेगा. तो एक क्वेश्चन मुझे पता नहीं आप लोगों के बैच में नहीं हुआ था, उसके पिछले बैच में आया था कि ये जो हर एक स्टेप में जा रहा है, परफेक्ट मैचिंग का साइज कभी चेंज हो रहा है, कभी चेंज नहीं हो रहा है, घट नहीं रहा है. सो क्वेश्चन इज, एक क्वेश्चन ये भी आया था कि ये 3 से क्या नेक्स्ट iteration में 2 हो सकता है. द आंसर इज नो, बिकॉज इट विल इंट्रोड्यूस मोर zeros, so it will keep on increasing. But can it remain same? If it remains same, is it possible that at every iteration it remains same? The answer is no, and that answer I cannot give to them. The reason is यहाँ पे जो cover value है, ये cover value keeps on decreasing on every iteration, strictly decreasing. So at some point in time, it will reach the maximum matching value, weighted maximum matching value, and at that time we have a perfect matching and we have the minimum weighted cover. Okay, so that is the discussion, and I will send you this slide, and I will add the proof of the lemma 2 also. I will prove the add of the lemma 2 also. बहुत सिंपल है, तो वो एक बार रीड करोगे हो जाएगा. मतलब इसका लेम्मा जितना बड़ा है, प्रूफ उससे थोड़ा सा बड़ा, एक स्लाइड में वो प्रूफ आ जाएगा. So with this, our matching chapter is covered, and as far as your midsem is concerned, you can expect questions from matching. Definitely we expect good questions from matching. इसके बाद हम लोग स्टार्ट करेंगे कनेक्टिविटी, जहां पे हम लोग एल्गोरिदम कोर्स में भी बोले थे कि जहां पे हम लोग बेसिकली बहुत एल्गोरिदम डिस्कस करें. इनिशियली कुछ प्रूफ्स हैं, बट बहुत सारे एल्गोरिदम्स हैं बेस्ड ऑन लाइक मैक्स फ्लो मिन कट. सो मैक्स फ्लो मिन कट के डिफरेंट एप्लीकेशंस पढ़ेंगे हम लोग, डिफरेंट, और भी फोर्थ फल्गर्सन से अलावा भी कुछ एल्गोरिदम्स है, वो हम वहां पे डिस्कस करेंगे. So lot of things, lot of algorithms will be discussed in the next chapter, and that is very important. So matching and connectivity both are very important chapter as far as your midsem goes. So with this I end today's class, and thank you.
Thank you.